Greetings and salutations, magical chemists. Let's talk about the common ion effect. Remember, solubility can change if you change reaction conditions. And Le Chatelier's principle predicts a salt will become less soluble in a solution if it already contains one of its own ions dissolved. This is called a common ion. The presence of a common ion acts like increasing the concentration of a product ion in the salt dissolution. This causes the system to shift left to establish equilibrium, moving towards the solid side, meaning that less can dissolve. Let's see how this works by looking at an example. First, we're going to look at and try to find compounds that would have a common ion for magnesium chloride. Recognizing, of course, that magnesium chloride will dissolve to produce Mg2+ and 2 chloride ions. That means either a magnesium ion or a chloride ion would be considered a common ion to magnesium chloride. So the following compounds, anything that either has a magnesium or a chloride, would have a common ion. So the silver fluoride, not so much. Sodium chloride, though, it has chloride ions. And then magnesium hydroxide has magnesium ions, and aluminum chloride has chloride ions. So it turns out, not the aluminum sulfide though. All right, so out of these 5 potential compounds, 3 of them would dissolve to produce a common ion to magnesium chloride. Now let's say in 3 separate solutions, we added each of those compounds, sodium chloride, magnesium hydroxide, and aluminum chloride, into a solution of magnesium chloride. Well, if we added all of them in equal amounts, which one would reduce the solubility of MgCl2 the most, and why? Well, you might have noticed when we were looking at these 3 compounds, they have a different number of common ions. Sodium chloride has 1 chloride. Magnesium hydroxide has 1 magnesium. But aluminum chloride has 3 chloride ions produced for every formula unit of aluminum chloride that dissociates. So aluminum chloride, if they're all in equal concentrations, aluminum chloride would be adding the most common ions and thus reducing the solubility of MgCl2 the most. As for the compound that would reduce the solubility of MgCl2 the least, well, those would be the compounds that don't contain any common ions because they're not going to affect the solubility. There are also other changing reaction conditions you could use to affect solubility. pH can actually affect solubility, but only sometimes. If you have a salt containing ions that can act as an acid or a base, the solubility of that salt will be affected by changes in pH. Let's consider the dissolution of iron 3 hydroxide as an example. Okay, first we want to know if iron 3 hydroxide would be more, less, or equally soluble if you put it in a basic solution. Well, here's the thing. You have to remember a basic solution by definition has hydroxide ions present, which are a common ion to FeOH3. So since you're adding more of a common ion in a basic solution, FeOH3 will be less soluble. We can also ask the same question about iron 3 hydroxide, but this time we can ask about its solubility in an acidic solution. This one's a little more interesting. Would you be surprised to find out that iron 3 hydroxide is actually more soluble in an acidic solution? An acidic solution, by definition, has a lot of H+ present. Well, those will react with the OH- ions, reducing their concentration. If you reduce the concentration of OH- ions, you're reducing the concentration of your products. That's going to cause the equilibrium to shift right, which will result in more iron 3 hydroxide being able to dissolve to reach equilibrium. I know you're probably thinking, this has been really conceptual so far, and you're wondering, where are all those tasty numbers? Well, worry not. We can do calculations with the common ion effect as well. Let's take a look at a couple of types of problems you might see involving common ions. The first problem type, a classic, says calculate the molar solubility of a given compound, but you're in a solution that already contains a common ion to that compound. So we're going to look at nickel 2 carbonate, but I want to know its molar solubility if it's already in a solution containing 0.1 molar sodium carbonate. Sodium carbonate, of course, is 100% soluble, which means you have just dissolved a bunch of carbonate ions, which are a common ion to nickel 2 carbonate. We are going to need a rice table for this. And it turns out we need a real rice table, not one of the tiny solubility rice tables that we've been making so far. Nickel 2 carbonate, of course, dissociates to produce nickel 2 plus and carbonate, which is CO3 2 minus. Up until this point, we've been starting off with 0 for the starting concentration of our ions, but that's not true this time. Remember, we started off with some carbonate, 0.1 molar to be precise. So our change, well, they both form one ion, so we're going to be gaining X, giving our equilibrium concentrations of nickel to be X, and of carbonate to be 0.1 plus X. So now we can go ahead and plug into our KSP expression. Now when you plug in for KSP, you get X times 0.1 plus X. You might be thinking, wait a second, isn't this like those circumstances where I can make some approximation? You would be right. And in fact, what you're looking for is an initial concentration, in our case, 0.100, that is more than 1,000 times greater than the KSP. Well, the KSP of nickel 2 carbonate is pretty dang tiny, so 0.1, while small, is definitely more than 1,000 times bigger. And because that is true, we can say X is negligible, which means KSP is about equal to 0.1X. And of course, we know the value for the KSP. It was 1.4 times 10 to the negative 7th. Since we're looking for molar solubility, we're just solving for X. So now it's just some easy algebra. So our molar solubility of nickel 2 carbonate in this 0.1 molar solution of carbonate ions is 1.4 times 10 to the negative 6 molar. You might be wondering, but wait, how much did it actually depress the solubility, the fact that I put the carbonate ion in? Was it just a little? Was it a lot? Well, let's just do a quick calculation. We can calculate the molar solubility of nickel 2 carbonate just in pure water. Well, in that case, our KSP would just be X squared. So if we take the square root of our KSP value, we'd find a molar solubility of 3.7 times 10 to the negative 4th. That's pretty crazy. You could dissolve a lot more if we hadn't already dissolved the carbonate ions. So this proves the carbonate definitely depressed the solubility. Okay, now I have one for you to try. I know you're excited. So go ahead and try this calculation on your own, and when you're ready to check, unpause the video. This time, we needed to calculate the molar solubility of strontium fluoride in a solution containing 0.4 molar sodium fluoride. Hopefully you recognize that fluoride was the common ion, and there's going to be 0.4 molar of it because, of course, sodium fluoride will 100% dissolve. Then we can go ahead and plug into the KSP expression and solve. Don't forget to square the concentration of your fluoride ions because 2 fluoride ions are produced per formula unit. You probably noticed that this was another perfect chance to use your approximation skills. Since the KSP value, even times 1,000, is still less than 0.4 molar, X is definitely negligible, so we can simplify this enormously. And since we know what our KSP value is, now we just solve for X. So we calculate a molar solubility of 4.9 times 10 to the negative 9th molar. Okay, so that's how you would calculate the molar solubility for a compound if you have a common ion already dissolved. There's another way that you can apply the common ion. You can actually use a common ion to achieve a desired concentration of a given ion. So let's see how that works. Basically, the trick is to dissolve enough of a common ion that it limits how much of the compound actually can dissolve. Now, these questions, when you see them, are going to look kind of complicated because there's a lot of words in them. But the funny thing is, these are actually relatively straightforward to solve. You actually don't need a rice table. Okay, let's look at an example problem. So in pure water, the KSP of calcium carbonate is 3.8 times 10 to the negative 9th. We're adding calcium nitrate to 1 liter of a saturated solution of calcium carbonate until the carbonate concentration is reduced to 2.3 times 10 to the negative 7th molar. This is the key. We're basically setting the carbonate ion concentration at this particular value. Well, this is like having an equilibrium constant expression where you already know one of the values of one of the concentrations at equilibrium, and you just need to solve for the other, because they told us what our KSP value was. So we just need to write our KSP expression and solve for the calcium ion concentration. That's it. Well, okay, technically they got a little more specific. They want to know how many moles of calcium nitrate would you need to add. Well, that's fine, but first we just need to figure out what the concentration of calcium would be by plugging in for the KSP expression. So let's try it. Since calcium carbonate dissociates to produce one calcium ion and one carbonate ion, well, the KSP expression is pretty straightforward. So now we just need to plug in the values that we know. Well, I don't know the concentration of calcium ions, that's the whole point, but I do know the concentration of carbonate, and I know the KSP value. So, with a little bit of algebra, I discovered that I would want the calcium ion concentration to be 1.7 times 10 to the negative 2 molar calcium. Okay, awesome. But now we need to answer the question, because they want to know, that's great, if I want that concentration, how many moles of calcium nitrate must have been dissolved? So we're converting molarity to moles. Well, that only works if we actually know the volume of solution, but we do, and look at that. It was even a nice, pretty volume, 1.00 liters. Of course, multiplying molarity times liters will get you to moles. So I have moles of calcium ions, but I want moles of calcium nitrate. Well, there's only one calcium in calcium nitrate. Remember, even if it's a 1-to-1 mole ratio, you still have to label your ratio and show your work. But of course, the math is really easy, no calculator required. So we would need to add 1.7 times 10 to the negative 2 moles of calcium nitrate. Okay, we have one more of these type to practice, but this time you're gonna try. So go ahead, try the problem, and when you get stuck or you're ready to check your answer, go ahead and unpause the video. Okay, in this problem, we have copper 2 iodate, and we're adding sodium iodate, and we want to reduce the copper 2 plus to a given concentration. Remember, if there's only 2 concentrations, and they gave you one of them, you don't need a rice table. You just need to plug into the equilibrium expression, KSP. Don't forget to square the concentration of your iodate ion. Oh, put that as a 2 minus. That's just awkward. There we go, because there are, of course, 2 iodate ions produced for every 1 copper ion. And then, of course, mathy math, and that will get you the concentration of your iodate ion. Once you find the concentration of iodate ions you need, the second step, of course, is figuring out the actual moles of your sodium iodate that would need to be added. Don't forget that there are 2 liters of solution this time. So you have to multiply your molarity times volume, and that'll get you 2 moles of iodate. And then, well, it turns out there's 1 iodate ion in every sodium iodate. So we must need to add 0.097 moles of sodium iodate to reduce the concentration of copper 2 plus down to that particular concentration. And there you have it. Thank you for playing with all of the glories of common ions and, of course, delicious chemistry.